11 watching, wow.
Huh. Oh.
That was fast. Did you even send out the link?
I don't know who those people
That's
are.
just the
Right. Water quality department.
Right.
What? Did you send out the link earlier?
I sent it out. I did, and I said it was 9:30 a.m. So that's
Okay.
But it's nice to see people are commenting.
Yeah.
Oh, it's funny. There's a delay. Oh
Yeah,
wow, that's weird.
It's like a 5-second delay.
That's what I was doing 5 seconds ago.
That's very bizarre.
That's so we can believe you.
Oh, this is weird. Wait, are we? Maybe we should turn off the audio on that.
Alright, we'll turn, you can close
Yeah, we
that.
might turn off the audio.
Yeah.
Alright.
Do you want to send that out to the list? Or I just sent something to Liz and her list. Do you want to send that to that email?
Sure.
Whatever the link is.
So if
Or put it in the email.
so this is our camera now, I guess.
Okay, so wait. You sent out the link earlier.
I did. I sent out an email with a link in it. But now that people are commenting, asking whether it's happening, maybe we could send out another email to the list just saying that we are live now.
Yeah, where's
People seeing just me staring at them.
Oh, sure, I found it.
Okay.
No worries. Okay.
And there's a link for the YouTube stream and a separate link for the Hangout.
Oh.
Yeah, and it's always Google's always changing it, but that's one thing that
YouTube stream is fine.
yeah,
I think.
YouTube stream. Yeah,
Yeah, 'cause I think
people would
it's very
watch it.
ambitious to have like live questions.
Yeah.
or something. Great. Okay.
Sure. Yeah, that's okay. Does that look like that?
Yes.
Okay.
Great.
Cool. Aha.
Ready when
Go.
you are.
Alright.
Oh, well, maybe I should say some administrative information, like the bathroom is that way and to the left, or that way and around, basically kind of directly behind us. There's water right there if you need it. There's coffee over here, but you need your own cup. So if you don't have one, ask Heather. We can try to find you guys cups. And we have a secret snack drawer over there, which I can point out to break.
Very important.
Great.
Okay. Alright, so my name is Jeff. I guess I'll tell you a little bit about my background. I got my undergrad at Cornell in Science of Earth Systems, and I kind of focused on biogeochemistry and hydrology and everything from kind of a science perspective, and then I decided that I really wanted to be an engineer. So I came here to MIT, got a Master's of Engineering over in the Parsons Lab, and they sent me to St. John to look at coral in January for our project. Pretty cool. And then I went to work at CDM, which is a consulting company right down the road from here, and I was there for 3 years, and then decided to get my PhD, so I went to Tufts, and ended up in kind of an odd topic for an engineer, which was to do web applications for modeling. Because it was kind of built out of my frustration with the current state of the modeling tools in our field, many of which still run in DOS and Fortran, and They work great, but they're really hard to use. So just kind of figured out a new way to put everything on the web. So that's what I've been doing. And so I thought, for this project, since we're going to be measuring water quality, and you got a lot of people with different backgrounds, to kind of show you how I think about it, and also how I visualize water quality data. So I'm going to talk a little bit about the science. I'm not going to talk too much because it's a little dry and kind of immense. But I'm going to cover some kind of fundamental topics, and then just show you a lot of examples of projects that I've worked on over the years involving water quality data. So, where did this field come from? Field of water quality. And my advisor, Steve Tapper from Tufts, gave a lecture here at MIT a few years ago. He called Rubbish, Stink, and Death. And I think he's trying to write a book, actually, with the same title. And
That's a great title.
it basically refers to the fact that there are three core problems with water quality. Rubbish refers to kind of the aesthetics. So that's trash and oil slicks, algae blooms, everything that makes water look nasty. Stink kind of refers to ecosystem degradation, because when ecosystems get overpolluted, they usually die and become pretty stinky. And then death refers to the public health aspect. And this image is...
sorry, it's motion. We just have to move around. I think.
And so there's actually a link. You can watch his lecture. It gives you a pretty good kind of history of water quality if you're interested. But it really dates back to the Thames, and that's what this picture is of, is the silent highwayman rowing across the Thames, and there's dead rabbits and things in the water, and there's a huge I don't know, I'm going to call it a stink event in 1860s, 1880s, when it was just putrid smelling, and people realized they had to do something rather than just dump all their sewage on the streets, and so that kind of gave birth to our field of water quality. So a little bit about the science of water quality. I think really you have to keep three. It's really the combination of three fundamental sciences: physics, chemistry, and biology. And when you're thinking about water quality, you really got to think about all three of those. It's not just the chemistry, because you have to worry about how is the water moving and mixing. That's a physical process. The chemistry is obviously the reactions that the compounds go through when it's in the water, and then the biology is a major factor, because it's all the bacteria that they'll convert nutrients to different forms. They produce pollutants. They themselves are a pollutant. You get ingest E. coli. But it's also the fish can control water quality by eating the phytoplankton and doing all that stuff. And birds can even affect water quality. It's a big problem in some reservoirs, is dropping into reservoirs, and their solution to that is to put a guy out there with a shotgun in a lot of cases, and it's pretty interesting. But that's water quality is really about these three things, and that's what attracted me to it originally, was because it's a complicated problem that involves a lot of different pieces. And the other way to talk about this is in terms of fate and transport. And so that was the name of one of my core classes I had to take, was fate and transport, and that's all about the math and the modeling behind the fusion and the movement of water and mixing, and then the decay of materials and everything. So you'll hear the term fate and transport a lot in water quality. What's the fate of the pollutant, and how is it transported?
Fate means where did it go? Is that
Yeah.
what it means, or?
So fate, this is a nice little diagram of a water quality model that's for algae growth. You have basically carbon, nitrogen, phosphorus over there, and phytoplankton, and dissolved oxygen. So you can see all the different pathways, how complicated this is. And so fate refers to, where do things end up? Some things go down, end up in the sediment. Nitrogen can get released to the atmosphere. Oxygen goes to the atmosphere also. there's all these different pathways. So how do the substances move between these different pathways, and where do they end up? So
in death, so we have organisms that are dying and entering the diagram where death.
Right. So if you have a cell of algae and it dies,
mm-hmm.
then basically it becomes nutrients.
Mm-hmm.
It'll get decomposed and become just organic. Oh, the O's that stand for organic, so it becomes organic nitrogen and organic phosphorus.
Okay.
And then that goes and can be reuptake through this whole pathway and become new phytoplankton. There's all these feedback loops too, which makes it interesting. But it's complicated. There's a lot of moving pieces.
And sorry again, if I had a farm that had a bunch of runoff, where would I put that in here? It would depend on what chemical I was.
Right.
External loading.
External loading.
Okay.
Yep. And then it basically would contribute to all of these.
Okay.
Right.
Okay.
Some more than others, but yeah.
Okay.
So this is just a nutrient algae growth model, basically. And so a little bit about why is water quality a problem, or when is it a problem? And it really depends. This is something that actually took me a few years to really grasp, is the fact that you can't just call something a pollutant, or you can't just call something a problem without specifying who, how much, and when. For example, phosphorus we think of as a pollutant, but phosphorus itself is not really toxic. We are made of a lot of phosphorus. Phosphorus is considered a pollutant because it drives algae growth, and that in turn causes other problems like low dissolved oxygen. One of the big problems around here is called Cyanobacteria, or blue-green algae. So this is a shot of the Charles, and the green in the water is this blue-green algae, which when it gets too much phosphorus in the water, then this algae just takes off and grows a lot. And it kind of affects the aesthetics, but the real problem is the fact that this algae produces neurotoxins. Mm. And when a dog, it's in which itself, if we go swimming in there, there aren't too many people who go swimming in the Charles at the moment, but there are a few. But it's a big problem for dogs in some areas, because dogs will just drink the water out of the river and they're ingesting neurotoxins and they can get sick and even die. So, getting back to what is the problem, phosphorus itself is not a problem. It's only a problem because it produces algae, and then the algae produce neurotoxins or cause other problems. And so you have to so it's really a challenge. Problems like low dissolved oxygen or neurotoxins. How much phosphorus can we let into the river? And that's a really big, difficult question. And the same thing with metals and everything. At very, very low levels, metals are okay, but there's certain limits. So when we talk about water quality problems, you always have to kind of put it in a context of what is the problem. Are you talking about a problem for human health or for ecosystem, type of thing? All right.
Sorry, just a quick pause. The audio is perfect, and but the screen is a little bright.
Okay.
So that it's hard to see the text.
Yeah.
This is what it looks like. Mm-hmm. Maybe there's some way we can.
You can post the link to the slides.
We have the link to the slides.
Links to the slides are in the document.
Yeah.
Okay, cool.
Yep. So, there's a lot of different types of pollutants, and a lot of different ways to categorize it. One of the most basic ones that I think will be useful for us in particular, the difference between conservative versus non-conservative pollutants. And basically what this means is that the conservative pollutant is something like salt, which doesn't really react with anything. It does, but not nearly as much as nutrients or other things. And so when you put salt in the water, it doesn't really settle out. It doesn't get degraded. It just sort of travels with the water. And another word for that is tracer. So we can use salt as kind of a tracer to see, where did the water that's in the river come from. I'll talk more about that at the end. Talk about conductivity. But a lot of other pollutants are non-conservative. So when you go out and measure them, you're not just measuring, if you measure phosphorus in the river, you're not just measuring the phosphorus that came off the land. You're measuring what came off. So that's a non-conservative, which is majority of pollutants go through are non-conservative. Another distinction is particulate versus dissolved. So a lot of like phosphorus, for example, will bind to soil particles. So if you measure phosphorus, you have some phosphorus dissolved in the water, and some of it is bound to particles. And clearly, if it's bound to particles, the particles want to sink. So it undergoes kind of different reactions and everything. And then you can just group different types of pollutants. There's nutrients, metals, pathogens, salts, organics like PCBs, turbidity you could consider a pollutant. It's just, there's all kinds of pollutants. And I don't think I'm really going to go into too much detail about it. The different sources, the two major sources are considered point sources versus non-point sources. Point sources is basically anything that comes out of a pipe. This distinction gets a little blurred when you talk about stormwater. Stormwater comes out of pipes, but it's also kind of considered a non-point source.
Really comes out of many pipes.
Yeah, it'll come out of many pipes. It drains a large area. Point sources are more like wastewater treatment plants. Like all the effluent from wastewater treatment plant will come out of a single pipe. And so when you look at the history of water quality, it was driven by the Clean Water Act in the 1970s, and they put all these regulatory mechanisms in place to control point sources. So now wastewater treatment plants discharge pretty clean water, at least a lot cleaner than they used to. In a large part because it's a lot easier to measure and also control what comes out of a point source, because you just have to measure one point. Non-point source is just runoff, and that's a lot more difficult because you don't know where it's going to flow or how it's going to flow, and it's just a lot more complicated. So that's kind of our big major challenge in a lot of ways is non-point source today. Yeah, that's all I'll say on that. So that's kind of the background. So now I'm just going to go through a bunch of projects that I've done over the years and show you how I used visualizations to really understand water quality data. And so the first, in the vast majority of my projects, the fundamental question is really about variability. So why do the concentrations change? And why do they change in space and also over time? This is probably, if I had to pick one thing that I was most interested in, this is what it would be, is understanding the variability of water quality concentrations and data. So I'm going to show some examples of different ways to look at this. Yes, timescales. You can talk about long-term timescales. So how does concentrations change over a long period of years? But water quality data also changes seasonally, because especially in temperate climates, because there's really nothing growing or doing anything in the winter. In the summer, everything grows. So you tend to see these cycles through the seasons. We can talk about event scales, so individual stormwater events. It'll rain, a bunch of water will run off the land and go into the river. That's sort of at a weekly time scale. And then you can talk about diurnal changes, so what happens over the course of a day. So I'm going to try to touch on each one of these in different examples. All right, so I'm going to go to the Everglades first, and we're going to watch a video. This explains what goes on down there a lot better than I could. So you get not coming off of houses and farms, and it goes into You can see them from space. So you see all the pollution goes into the reservoir, and then it goes down this canal. And over here, so they built a wetland. It's thousands of acres in size, and basically the idea with the wetland is to use plants that happens in the Everglades. And this is a major project. It's spent billions of dollars since the 1980s to build these.
I think
Your experience was?
It's a good setup.
What's the scope of those wetland projects?
Like how much like how big a city could how much wetlands take care of take care of the weight of their waste?
pretty big. I mean, these are massive, massive wetlands. They use like super sized bulldozers and everything. It's really cool. You can see a lot on the web. But they don't. A lot of it is actually designed to treat not so much city runoff down there. It's more the farms, citrus groves and sugarcane and everything. Because that they dump a lot of phosphorus. But now the cities are becoming more a problem because they've actually addressed the farming problem to some degree. But I don't know. That's a good question. I don't know how much of the total water that gets into the Everglades passes through those wetlands. I don't think. I mean, I would guess like 10% or something.
Okay.
I don't know.
Okay.
It's not like it's treating all the water.
Okay.
It's just trying to treat the dirtiest water.
And it started in the 80s. So does it take a long time for the kind of filtering that happens in the wetlands to kick in, or is it something that you see as results pretty immediately?
I think it takes like a year because when they build them, it's just bare dirt, and then they plant vegetation. And some of the questions are, what kind of vegetation do you want to have out there that take up the phosphorus? But it usually takes about a year, I think. Before they're kind of established. So when you build them, it's kind of, you gotta try not to generate a lot of pollution just to get started. But
and how unique is that situation because of the built infrastructure, like the canal system that you have in place to sort of route everything to a central place?
Yeah, I mean, that was a big.
Yeah,
I mean, I'll show you in a minute the consequences of that. But yeah, down South Florida, it's all canals that they built over the years. So they've totally changed the hydrology because it used to be that we called the mile-wide river or something because basically water would spill out of Lake Okeechobee and just flow as one really wide, really shallow river all down through the Everglades. And then they cut up all the canals and everything, so now the hydrology is totally changed, screwed up the water quality also. And they're trying to get back to kind of natural conditions, but they'll never quite get there. So here's all our data. So, this is kind of always how a project starts. We get the data, and we look at it, and there's, again, two questions. What are the spatial gradients? And also, what are the long-term gradients? Are things getting better or worse? So you can kind of look at this, and I don't know. It doesn't really tell you a whole lot. You see some patterns.
And what is it?
So this is all going to be phosphorus data.
Okay.
One thing I'll note is that I pretty much always use log scales for water quality data because it's log normally distributed, which means that it usually has some values that are a few values that are really high, and most of the values are kind of low. Got a long tail to the distribution, so if you put it all in a log, it's a lot easier to look at. And also to do the statistics and everything, you should do a log transform. But so we can take this data, and one way to look at the gradients is to kind of just order these from upstream to downstream and just look at the distributions of each station. So now on the x-axis is each station, and I just took all the data over time and just made a box plot.